So what I want to do is look at parametric surfaces and then the areas of them. Basically what we're doing is we're taking a surface and we're parametrizing it using two variables, sometimes u and v, sometimes phi and theta, sometimes x and y. It will really just depend on the application, because what we want to do eventually is to do integration on surfaces. I'll find it here in a second. We're going to do surface integrals, and this is in 16.7. And in order to do those, we will need to parameterize the surface R. In this case, it's R of UV. So what I want to do is I want to first go back to something that you have seen before. And so before, what we did was we parameterized curves. So what you had was you had some curve in two space. Well, let's say three space. A curve in three space, like this, going out like this. So see, was this curve, and it always had an orientation to it. Let's suppose it goes from left to right. And in order to get that curve, in order to parameterize it, we used a parameter t. We used points on the x-axis, or points on the number line, excuse me, either one, points on the number line, and we associated them to points on the curve. So like this. And that association we called R of t, like this. We used t. We didn't always use t. We could have used theta if we wanted, or x, whatever. The point here is that if you stretch out c, if you stretch it out, you pull the ends of it, let's say, just informally, you get t back. You get this number line. So it's a one-to-one correspondence. One of the examples of this was like R of t, and you had like x of t, y of t, and then z of t. So examples of this were like, I don't know, cosine t, sine t, and then t. This was the helix. All right. So the idea was to pull numbers, a single number from the number line, and then associate that to points in three space. So you associate it to a point in three space, and then you do that for all the numbers which apply in the domain of R of t. So for example, if you did R of, I don't know, let's say R of pi over 2, that would have been 1, 0, I'm sorry, 0, 1, 0, 1, and then pi over 2. And so you have a point in space, 0, 1, pi over 2, that's associated to pi over 2. So I don't know where that is, maybe over here somewhere. Okay? All right, this is a helix though. All right, so that was a curve. So if we want to parameterize a surface though, if you flatten out the surface, like over here when I said you flatten out the curve, you pull the ends, you get the number line. So there's a one-to-one correspondence. You get a correspondence between the two. But here, if you flatten out the surface, you're going to get a region in space. For example, if you take the bowl, all right, take the bowl, upside down paraboloid, like this, or maybe a half sphere. If you flatten this out, you're going to get a circle, okay? So it's not possible to take t values from a number line and associate them to a surface and expect to get the whole surface back with one parameter. So we're going to require two in this case, two parameters. All right, so since there's two parameters, what's happening is you start out with something with a region in the xy plane, or R2 if you want. You start out with a region in R2, and to that you associate, to every point in there, you associate a point. Let me use a different color. You associate a point in R3. Okay? So you may have something like R of UV is U V squared, and then U minus V, something like that. So the point let's say, I don't know, what does this point look like? Let's say 4 comma 1. 4 comma 1 would be mapped to 4, 1, 3. That point there. So you go out 4 over 1 up 3, and it's point, so it's mapped to that. All right, and we use vectors to do this if you want. Vector notation if you want. All right, so that's how it's done. Now, in order to find out what these are, if I give you a parameterization, like here, if I give you this parameterization, I hate the IJK stuff. R of UV just gets in the way. It's 2 cosine U V and then 2 sine of U. And then there's going to be limitations to this. All right. In order to figure out what this thing looks like, you kind of you try to see if there is a correspondence between X, Y, and Z. So let me pull this over and let's look at this. Okay, so here we are. So we have the X, we have the Y, and we have the Z here. All right. So it looks like X squared plus Z squared is 4 cosine squared U plus 4. So we have 4 sine squared U here. And so this is just X squared plus Z squared is 4. All right, so that's the case. Now, there's a bunch of V's going on here too. So for every V value, we have a new circle. So what we see here is there is a circle in the XZ plane when V is 0. There is a circle in the, let me just do this. There's a circle in the, so like, for example, so this would be like when V is 0. And this would be like when V is 1. When V is 1, this is Y, right? So Y is 1, Y is 0. These are planes. So let me draw this a little better. So then another circle when V is 2. Okay? So it looks like we're mapping out a cylinder here. All right, now let's take it whenever, let's suppose that maybe U is constant. So let's see what happens when U is a constant. Let's see. So U is constant. Say U is, I don't know, 0. So when U is 0, we get, I'm looking at this, we get 2 V, and then let's say, so then that's 0. So Y, this is X, Y, and Z, right? So when X is always 2 in that case, so here's 2. Y is V, so as V, your parameter V varies. Remember, all this comes from the UV plane, right? Some region in the UV plane. So we're looking at when V varies. So V is some numbers on the number line. So when V varies, we get a new Y value. And so that would be all of this right here. Because these are Y values, right, in that direction. So we get this line right here. So now let's say that U is, I don't know, U is pi over 2. So then we get, let's look at the original, pi over 2. When U is pi over 2, we'd get 0, V, and then 2. So that's the line. So this is X is 0, Y is V, all the values of V, and then Z is 2. So Z is always 2. Remember, this is a circle of radius 2, right? So when Z is 2, that's here, and then Y varies with V. So V is 1, V is 2, V is 3, V is 4, V is 5. So what happens is, for every U value it looks like for every u value we we denote as, see, whenever we hold u constant, all right, we have different u values, we get a new line that's going along the y-axis like this, get a new line. So it looks like what we're graphing out is a cylinder. All right, as a cylinder. So these are called grid lines, or grid curves if you want. So the circles are when v is constant, and the lines are when u is constant. Now there was a restriction here. U goes from 0 to pi over 2, and v goes from 0 to 3. So when u goes from 0 to pi over 2, when u was so when u was constant, we got those lines. All right. So it looks like it's going to be the half or a quarter cylinder, like this. And then it stops where v is 3. So it's this right here. Alrighty, so these lines that we've drawn here, the circles and then these lines, these are called grid lines. And this is where u is a constant. We alternately let u be a constant and then v be a constant. And so you'll see this in how things are graphed in Mathematica and other programs like Wolfram Alpha. So you're pulling your values from your region. This is your domain. You're pulling your values from your region, and you're graphing them, you're plotting them to values in R3. All right, in R3. Now, one way to do this is to use the grid lines. Okay, so let's try this. Try this on for size. So essentially what's happening is if you let, so this is u down here, if you let u be constant, you get this graph right here. You mean this line right here. If you graph that line using your r, so this is r of uv, you're going to get some curve in space. Now, as you graph more of those, you get more curves in space, like this. Keeps going. Now, let's do the same thing for v. Now, this is v here, so when v is a constant, we get the curves going the other way, like this. Okay? And so what Wolfram Alpha and Mathematica do is they shade in everything in between. So these are curve lines for u being constant and v being constant. So u constant are these circles. This is a different graph. U being constant are these circles right here. And then v being constant are these helixes, like this. And you can see this in the expression for the parameterization. So I'm gonna take this and well, I tell you what, I think I can work with it right here. I have room. So let's let u be I don't know. Let's let u be 0. So then r of 0v is 2 plus sine v. Cosine of 0 is 1. Sine of 0 is 0, so we get 0 here. And then u is 0 gives me cosine v there. Like that. Yeah. So here, if you look at x and you look at z here, x and z here, we have x equals 2 plus sine of v, or x minus 2 equals sine of v. And we have z equals cosine of v. So when we do x minus 2 squared plus z squared, we get 1, because that's sine squared plus cosine squared, right? All right, so this is a circle of rate of center 2 comma 0 in the xz plane with a radius of 1. All right, so that's where y is 0. So it's going to be this circle, like maybe right over here. Now, whenever you take v to be a constant, so let me erase all this. When you take v to be a constant, you'll see that we have helixes, or helices if you want. So let's see. Let's say v is 0 this time. So we get r of u comma 0 is sine of 0 is 0. So we get 2 cosine u comma 2 sine u comma u. Because v is 0, oh, u plus 1, like that. So here we go. So this is x, this is y. So x squared plus y squared is 4. And then z is u plus 1. So z varies according to what u is. So z is alternately 1, 2, 3, 4, 5, and then all the negative numbers 2. And then you have x squared plus y squared equals 4. Well, that's just a helix. We saw that before. So what that describes is a helix. So when you, let me borrow some room. Remember, a helix, you can describe it. It goes like this. It's a circle in the xy plane, but then as you draw the circle, you are moving up according to what u is. So when yeah, so it's like this. And that's going to describe these helices. In a way, I mean, it's not exact, but that's kind of what you do. All right, so that's that. And then there's some graphing. So what you should do to figure out which graph goes to which equation, which parametric set, is you should use grid lines. Let u be a constant, and then let v be a constant, and see what happens. All right, so for planes, I'm going to let you read this. It's really not hard. It's A and B are vectors that form the plane. Okay, and so when you have two vectors that are on the plane, you can make a linear combination of those to form the entire plane. So essentially, r of uv would be r naught, which would be 0, -1, 5, and then plus u, and then the a vector 2, 1, 4, and then the v vector, the b vector, sorry, -3, 2, and 5. All right, so in this case, you just add all this up. All right, so you would get 2u comma plus -3v comma, and then -1 plus u plus 2v, and then 5 plus 4u plus 5v, like that. And now that is your plane. Now we dealt with planes before where it was n dot r minus r naught. But this did not give a parameterization. This usually gave something using x, y, and z, like this. So a parameterization will allow your x, y, and z to be determined by two parameters in this case. And so it's a lot more robust. Now, if you look at how to parameterize a sphere, we can just use our rules from are spherical coordinates. So remember, from spherical coordinates, you had x, we're talking about the conversions, rho cosine theta sine of phi, and then y was rho sine of theta sine of phi, and then z was rho cosine of phi. So in this case, what they're parametrizing is this sphere of radius a. So r is a in every case. R is a. In other words, rho is a. So all you have to do is substitute a for rho, and you've got your parameterization set. So here we're not using u and phi. We're using phi and theta. It doesn't have to be u and phi. The conversions in polar coordinates from x, y, and z to phi and theta work just fine to parameterize the sphere. So very simple. And so what's happening here is the equivalent of what we did up here, where we started with a region and we ended up with a surface, is this time now the region is a rectangle, and we're going to end up with a sphere out of this. All right. Now the rectangle grid lines, so the constant lines for the rectangle. So notice the rectangle is phi and theta, as it's the rectangle in the phi theta axis. So when phi is a constant, like this, oops, let me use red. When phi is a constant, we should get a constant over here. So it turns out that when phi is a constant, we get latitude lines. Remember, the way you remember is it's a ladder. The latitude lines form a ladder as you walk up. All right, so when phi is constant, let's say phi is, I don't know, pi over 2. No, let's just say pi over 4. Ew, no, that's going to be gross. Let's say 0. So when phi is 0, we get 0, 0, and then a. So that's that point up there. So when phi is 0, that is right here. So that's that whole line is mapped to that little circle, that little point there. And then as we move to the right, we get more and more circles. So let's just do phi equals pi over 4. All right, so what we would get is a, okay, so phi is pi over 2, a root 2 over 2 cosine theta, a root 2 over 2 sine of theta, and then a root 2 over 2. So when you square these middle ones here, this is x, this is y, you'll get a root 2 over 2. You'll get x squared plus y squared equals a root 2 over 2 squared. And then you're moving up a value z, a root 2 over 2. So you'll get something like this here. And then as you go to pi, you're going all the way down to the bottom. So you continually make these. All right, now if u is constant, on the other hand, you're going to get something different. So when u is constant, I mean, sorry, not u, theta. Theta is constant. Let's say theta is 0. So theta is 0. We get r equals, so I'm looking up here still, r is a sine phi, comma 0, comma a cosine phi. So it looks like here's x, here's y, here's x and z, sorry, z. Y is 0. So we get x squared plus z squared equals a squared. So now that is a circle in the xz plane. So, well, that will be, when y is 0, is this here. And now, as we allow theta to change, the y component, here's the y component, is not going to be 0 anymore. It's going to move out. And so you're going to get other circles here as well. So I'll let you look at all that yourself. Okay, so what this says here, which is kind of cool, is that if you graph a sphere using the traditional equation for a sphere and solving for z, and then graphing both the top and the bottom, a computer can't really handle it, but it can handle it if it's using parametric equations, the same ones that we did in the previous example. Sphere comes out really nicely. All right, so here, example 3 says find parametric equations, a representation for the part of the sphere that lies between two planes. Now, z is rho cosine phi. In this case, rho is 4, so this would be z equals 4 cosine phi. And so when z is -2, you just -2 equals z. And so cosine of phi will be -1/2, which means that phi is going to be 2 pi over 3. All right. And then you do the same thing for 2, and you'll see it. So essentially what you have is like something like this, where the sphere would have continued on up here and then down here. All right. And the same thing for that. It's very similar. Okay. Oh, that's pretty straightforward. Surfaces of revolution. If you look, whenever you did technical difficulties here. Whenever you did surfaces of revolution in Cal 1, you did something like this. You did you had x and y, and you had some graph. Let's say it's square root of x, y equals square root of x, and then you rotated it around the x-axis like this, and then you found the volume. Now you found the volume, but you never found an expression for that surface, because that's in 3D, and Cal 1 didn't involve 3D, or you did it in Cal 2, same thing. So now I want to find an expression for that surface. So I'm going to look at it, the same thing in 3 dimensions. So I have y equals square root of x here, and I'm going to rotate it around the x-axis like that. And now that I have a z-axis, I can work with it in order to get a representation, a parametric representation of the surface itself. So what I'll do is I'll use the formula that they gave, was r of uv, in this case x theta. Well, let me just show you what it is, and then I'll explain it. R of x theta will be x and then f of x. I think I want cosine here. Yeah, cosine theta, comma f of x sine theta, like that. So here, what's happening is here's the y and z coordinates, y and z here. Y squared plus z squared is f of x quantity squared, okay? So that is a circle of radius f of x. So what's happening is in parallel to the yz plane, we have circles of varying radii. The radius is f of x. So in this case, f of x is square root of x. So I have a circle here, and the circle here, the radii are getting bigger and bigger. And so that traces out the surface, and so we can use the parametrization x theta. This will be x root x cosine theta, and then root x sine of theta, which I think is kind of cool. So that's how you do surfaces of revolution. Now, tangent planes, I'm going to let you go through this, but basically, whenever you have a parametrization r of uv or x theta or whatever, in order to find the tangent plane, you're going to do r sub u cross r sub v, and you find that'll be your normal vector. All right, and so what you're doing here basically is you're looking at a little piece of your surface. Say it's this. This is a little piece of your surface, and you have a vector here and a vector here that form the tangent plane to that surface that approximates it very well. And in order to find the area here, okay, in order to find the actual tangent plane itself, you need the cross product of these two vectors, which will give you your n vector as before. It's perpendicular to both of those. And the length of that n vector, that n vector will allow us to use our good old friend n dot r minus r naught, like that. And we can get the equation of our tangent plane out of that. Now, it's a little different for this. Like, if you see this is in the book, so I'm going to refer you to the book to look at that. All right, the surface area, very simple. You just, the surface area is, you're going to take all these areas of these little tangent planes and add them up. Well, the area is the length of n, right? Well, the length of n is just the length of RU cross RV. And so you add them all up and you get your area of your surface. So it'd be nice if you memorize that. I'll give it to you on a test, but the area of the surface is the double integral over d of RU cross RV dA. Now d is going to be the shadow of the surface in the xy plane. Okay, so it's going to be the shadow of this guy in the xy plane. Remember, that's d. All right, and I think that does it. Oh, one last thing. If your surface is described using z, then x and y can be your two parameters. It doesn't have to be this u and v business. So, for example, if you have z is x squared plus y squared, that's the paraboloid, right? It's a paraboloid. Then the parametrization can be r of xy is x, y, and then x squared plus y squared, like that. Or if you like u and v, you can just use those two, u, v, and then u squared plus v squared, like that. No problem at all. I mean, if your surface is given like that, definitely parameterize it like this. All right, and then your area of the surface will be this. Let's check this out. So if you notice, that's different than this. All right, area of the surface is that, and then area of surface is this. So let's just let's derive that real quick. So if I have z equals f of xy, then this means that z sub x is f sub x, and z sub y is f sub y. So let's see. Well, actually, I don't need that. If z is f of xy, r of xy is x, y, f of xy, like that. All right. Now let's do r sub x. That's basically r sub u. Okay, so r sub x is 1, 0, f sub x at xy. And then r sub y, let me just use f sub x, because you know it's of xy. So f sub x. R sub y would be 0, 1, f sub y. So now when you do the cross product, you get negative f sub x, negative f sub y, and then 1. So this is n. That's n. And the magnitude of n is, so you have your two vectors, right, that form a plane. And then n is the vector perpendicular to both of them. That's n right there. So the magnitude of n is the first one squared, f sub x squared, plus the second one squared, plus 1. And so we add all these up, and we get the square root of f sub x squared plus f sub y squared plus 1 dA over d. So remember, you have your surface over something like this, and you want to find the area. The area underneath, we're going to call d. That's the area underneath. You're integrating over that. Okay? All right. So that's how they get, where am I at? That's how they get this here. And then now it's going to be important that you know what n is. All right? N is this. We're going to need this in the next section. All right, that's it.